Hello everyone. Today we'll talk about the solution to the problem shortest subarray with sum at least k. The crux of this problem is that the numbers in our array can be negative, which means that a standard two-pointer approach is not likely to work. You can imagine a situation where for this starting position, this is the closest ending position that creates a correct array, but now by moving to the right with the starting position, the ending position can suddenly become closer. That will happen if the sum of this portion of the subarray, so this subarray, this portion here, will be negative. That might make it easier for us to push the end to the left. And that means that if we push the left end forward, the right end can be jumping to the left, to the right, to the left, to the right, which makes two-pointer approaches difficult, because for two-pointer approaches we typically want the pointers to be moving in a single direction. So that is one difficulty. But it doesn't mean that there is complete chaos in what's happening here. And in particular, when we have a ending position, I'm speaking once of starting, once of ending positions. Now I switch to ending positions because this is the implementation that I have here. But if there are two starting positions that we are thinking about, then what can we tell about the sum of the subarray between those two starting positions? Well, that sum can be positive or not be positive. But if that sum is not positive, so we don't gain anything by adding this portion to the thing that we have here, then there is no point in thinking of this ending instead of this ending. The only reason for us to think about this ending is if this block is positive, because it might mean that this subarray is not yet with a sum of at least k, but by adding this portion we get closer to k, or maybe we exceed k, which means that for ending positions that are the furthest to the left, those will have to be those with the biggest sum. So we're interested in the one that will give us the biggest sum. And now, because we don't really know what the sum is, that sum will change by pushing the right hand forward. Instead of trying to maintain that sum explicitly, we might just maintain prefix sums of the whole array, because prefix sums allow us to calculate the sum of any subarray. And since we want to order the left ends somehow, by ordering them based on which one gives us the biggest subarray sum, that's the same thing as the one that gives us the smallest prefix sum. Preferably that prefix sum should be negative. But the one that gives us the smallest prefix sum is the one that will give us the biggest subarray sum. So we're interested in the one which has the smallest prefix sum before us, and then the one that has the smallest prefix sum from among those that are to the right of it, because those to the right are preferable. They will give us a shorter subarray. So the only reason for us to care about this one is if they give us a shorter subarray but also a larger prefix sum, so a smaller sum within it. And this is a standard recipe for a monotonic stack, because we'll be maintaining only those interesting left points and updating it so that they still have this order maintained, that they increase, they get more to the right at every step, and their prefix sums unfortunately have to increase. So in this case we'll be looking only at some starting positions, but only those that are interesting, that are not dominated by some other position, so we'll find the result by looking at them. And one other thing that we can pay attention to is the fact that if we have a starting position, then we're interested just in the first ending position that creates a correct subarray. So if a correct subarray can be created from this start with this end, then we don't care about any ends to the right, so we should forget this start. And also, if a correct subarray can be created from this start and this end, then it can be created for all the starts to the left of it. Because those starts, they will give us a longer subarray, which is not good. But as we mentioned about this ordering, the sum will be even better. So if the sum is good enough here, then it will be even better for those to the left. Which means that we only want to remember the first end that creates a correct subarray. And after we see that first end, we can forget about the starting position. And that means, and since if we can satisfy a starting position, we can satisfy all the starting positions to the left of it on our stack, we can only look at the leftmost and keep looking at the leftmost, removing the leftmost for as long as it's possible to create an array. And that allows us to calculate all of this stuff, this monotonic stack that has elements added to the right and also somehow removed from the left, by using a double-ended queue, a deck. So this is the implementation that uses a deck, which we'll walk through now. To calculate prefix sums, that's of course very simple. We'll start with a 0, because we want to be able to include the first element. So the 0 represents the empty prefix sum for the empty prefix. And for every element, we take the previous prefix sum plus the element appended to the prefix sum array, and now we have that array. And to calculate the sum of any subarray, so for instance subarray between I and the first candidate, we just subtract their prefix sums. So that's why we're going to be using them. And of course, we want our candidates to be kept on a deck, and we go through the ending positions as we mentioned before. And there are two stages. The first stage is to create a good subarray. So we'll have a while loop that while there are some candidates, it looks at the leftmost candidate. So that's the candidate that's the furthest to the left. So the one that will give us the biggest possible sum or the smallest prefix sum. We compare the sum of the subarray, so the difference between prefix sum at our position and at the candidate position. If it's good, so if it's greater than or equal to k. If it's good, then this is the first right end for this left end, and the length is I minus the index of that left position. So this is a possible new result. And we get rid of that left candidate because we've already found a good right end. No further right end is better than that. And now we have to add our element to the candidates to the right, because maybe this position will be the starting position of a good shortest subarray. But before we do that, since we want to make sure that there are no pairs that one dominates another, that this is a monotonic stack, we'll have to get rid of elements from the right of our stack. So again, while there are some candidates and the candidate at the end is worse than our candidate, so again, what does that mean? Our position is to the right. So the only reason for us to remember a position to the left, a position that generates a longer subarray, is if that subarray generates a bigger sum of the subarray, so a smaller prefix sum. So if the prefix sum that they have is not smaller than our prefix sum, so the prefix sum of that candidate is greater than or equal than our prefix sum, we don't have to care about them, because for any end to the right of us, it's preferable to take us and not them. So we get rid of them from the monotonic stack. And at the end, of course, we've been asked to return -1 if there are no subarrays, so we verify that result has changed. If not, we return -1, otherwise we return the result. So this is a nice example of a problem where there is a monotonic stack. We have to update it from both directions, but we can do it by just using a double-ended queue, which allows us to do exactly that. And still the structure of the monotonic stack is pretty easy to understand. It has the standard monotonicity that we usually see in problems with monotonic stacks.